The first time I heard the word prototype was in design patterns. Today, it seems like everyone is saying it, but it turns out they aren't talking about the design pattern, the gang of 4 design patterns. We'll cover that here, but I'll also show you other more interesting places where the term prototype and the concepts behind it have popped up. But first, let's revisit the original pattern, the prototype design pattern. I don't say original lightly here. Design Patterns cites Ivan Sutherland's legendary Sketchpad project in 1963 as one of the first examples of this pattern in the wild. While everyone else was listening to Dylan and the Beatles, Sutherland was busy just, inventing the basic concepts of CAD, interactive graphics, and object-oriented programming. Watch the demo and prepare to be blown away. So this demo is, I don't think I want to watch it right here, but I will link. Copy link to location. I will give a link to that if anybody is interested. I will probably watch that at a later time. The prototype design pattern. Pretend we're making a game in the style of Gauntlet. So this might age some people out. Gauntlet was a game a long time ago. Was that for like the original Nintendo? Super Nintendo? It was a top-down sort of like dungeon explorer, almost like Diablo-like. That's sort of what I would describe it as. Precursor to Diablo style games. You had to go find something, and then that would move you to the next level, and you could play as one of 4 classes. It was very fast-paced, very high, very easy to get killed. Classic game of those times. We got creatures and fiends swarming around the hero, vying for their share of his flesh. These unsavory dinner companions enter the arena by way of spawners, and there is a different spawner for each kind of enemy. For the sake of this example, let's say we have different classes for each kind of monster in the game. Ghost, demon, sorcerer, etc. Okay, so we have a class monster, we're gonna do stuff, and then we have class ghost, which extends monster. So because this is C++, that's the reason why I'm going to. So I guess we're just gonna call this monster. So if we do monster.js, this is the equivalent of like class monster. It's going to do stuff, and so then if we have like a ghost, a demon, or a sorcerer, that would be, it extends monster like that, and so on for these other ones. So demon, sorcerer. Guess I should change this away from. I'm gonna put this all in one file so it'll be easier to see, and like, the editor to like do auto completion for us. So let's rename you to prototype. A spawner constructs instances of one particular monster type. To support every monster in the game, we could brute force it by having a spawner class for each monster class, leading to a parallel class hierarchy. So we have monster, ghost, demon, sorcerer sort of is feeding into that. We have a spawner, ghost spawner, demon spawner, sorcerer spawner. I mean, that makes sense. It's, in parallel to that. I had to dig up a dusty UML book to make this diagram. This arrow means inherit from. Implementing it would look like this. Class spawner. Okay, so we have a public. We're making the spawner if it's the same name, I believe that's the constructor. So they're making a constructor, a public, and then the monster, which is a spawn monster, which will return a monster. Then okay, so that's all for the spawner here. So this is basically a constructor. So that's just adding. Oh, I guess they're changing from monster to now we're going class spawner. They have a constructor. They're not doing anything with it. They're just sort of leaving that there. They also have this inside of here, a spawn monster method. So spawn monster method that itself is unimplemented. But now we're going to have a class ghost spawner that extends the spawner, which means that it gets this spawner method. Sort of like, now we're kind of like implementing an interface for this. JavaScript doesn't have interfaces, so this is as close as we're going to get. So public virtual monster spawn monster returns a monster and return new ghost. Oh, right. Okay, so we have ghosts like this. So we do still need these. So this is basically, is it like a factory pattern almost? Where this is going to create classes, instances of classes for us. I guess factory creates a class, right? A dynamic class. So class, we are going to have spawn monster, and this returns a new ghost. Then we have demon spawner, and that does exactly the same thing. And this returns a new demon. Unless you get paid by the line of code, this is obviously not a fun way to hack this together. Lots of classes, lots of boilerplate, lots of redundancy, lots of duplication, lots of repeating myself. The prototype pattern offers a solution. The key idea is that an object can spawn other objects similar to itself. If you have one ghost, you can make more ghosts from it. If you have a demon, you can make other demons. Any monster can be treated as a prototypal monster used to generate other versions of itself. To implement this, we give our base class monster an abstract clone method. Okay, so here in monster, we're going to have a clone method, it looks like. And it's going to return a type monster probably. Let's see. Each monster subclass provides an implementation that returns a new object identical in class and state to itself. For example, so each monster subclass provides an implementation that returns a new object okay. Oh, in state to itself too. Interesting. So it clones its internal state. Okay, so we have class ghost, for example, here. Public monster. So it returns a monster, it's public. So here's its constructor. So we're gonna have a constructor that takes in health and speed, for example. And it's going to put that inside internally. So the equivalent to this is this dot health equals health, this dot speed equals speed. Okay, so we create that. Now we have this virtual monster clone. So we have to do that from here. So we have clone. Clone doesn't take anything in, but it is going to say, okay, so virtual monster clone, return new ghost. So you're going to turn a new ghost and then pass that in, this dot health, this dot speed. And then private int health speed. Right, okay, so we're just saying that these two are private. Well, can't really do that in JavaScript. Let's save that one, okay. Once all of our monsters support that, we no longer need a spawner class for each monster class. Instead, we define a single one. So class spawner. So we have a class spawner, and we're no longer going to need these other spawners here. So I can comment them out, it sounds like. Public spawner. So looks like our constructor is going to take a prototype and store that inside. So we're going to have a prototype. This dot prototype equals prototype. And then we're going to have a spawn monster that returns a monster, which we have right here. And we're going to return prototype, this dot prototype dot clone. It internally holds a monster, a hidden one whose sole purpose is to be used by the spawner as a template to stamp out more monsters like it. Sort of like a queen bee who never leaves the hive. So that is interesting. So basically we're going to have a monster that's never hidden. So we're not cloning monsters that are out in the field. We're just like, you know, caging a monster and using it to create more ones. So spawner monster, the prototype, clone, and then yeah, monster. To create a ghost spawner, we create a prototypal ghost instance and then create a spawner holding that prototype. So monster, so okay. Ghost prototype, ghost spawner equals new ghost, new spawner. Okay, so a ghost spawner. Okay, so we're gonna create the ghost prototype. And then I guess okay, you're right. Then we spawn off of that. So we create just one off of the ghost. So down here, we'll just maybe say like in main, or like in our main library when we're initializing, I don't know where that specifically would be. We are, I guess, in setup. We're gonna say const ghost prototype equals new ghost, and then we're going to give it its health. So in this case, its health is 15, its speed is 3. And then we're going to create the spawner. So const ghost spawner equals new spawner, and we're going to pass it in the ghost prototype. And if we're talking about Rust type things, it's okay if it consumes this spawner, because we don't care about that anymore. This spawner, I guess it consumes the ghost prototype, and we're now only caring about the spawner. Which then I guess means that in our loop, we're now going to be able to have our entire, like all of our ghosts, right? So somewhere else we have like our ghost loop, our ghost like array of ghosts. Ghosts dot, I know it doesn't exist, don't worry about it. Dot push, and we're gonna do a ghost spawner dot clone, like that. And if we do that every single frame, we'll get a lot of them. One neat part about this pattern is that it doesn't just clone the class of the prototype, it clones its state too. This means we could make a spawner for fast ghosts, weak ghosts, or slow ghosts just by creating an appropriate prototype ghost. I find something both elegant and yet surprising about this pattern. I can't imagine coming up with it myself, but I can't imagine not knowing about it now that I do. There's some ideas that I have like for implementing it right off the bat, but at the same time, I'm not sure if it's like the right ideas. Like the trees could potentially be in a spawner. Especially if I have like different types of trees. We could have obstacles, and so that way it's we're creating them randomly instead of just sort of evenly throughout. How well does it work? Well, we don't have to create a separate spawner class for each monster, so that's good. But we do have to implement clone in each monster's class. That's just about as much code as the spawners. There are also some nasty semantic rat holes when you sit down to try to write a correct clone. Does it do a deep clone or a shallow one? In other words, if a demon is holding a pitchfork, does cloning the demon clone the pitchfork too? Also, not only does this look like it's saving us much code in this contrived problem, there's the fact that it's a contrived problem. We had to take as a given that we have separate classes for each monster. These days, that's definitely not the way most game engines roll. Most of us learned the hard way that big class hierarchies like this are a pain to manage, which is why we instead use patterns like component and type object to model different kinds of entities without enshrining each in its own class. So this goes by something that I saw recently in an Uncle Bob class, which is using object-oriented to describe the world or model the world isn't the proper way of using object-oriented. So we don't, I guess like the basic tutorials, we're always creating a car. Like, okay, we have a class for automobile, and a class for motorcycle, and a class for truck. And they extend from each other, and then we have like properties for fuel and speed and how many doors it has and things like that. But in modern times, it looks like the object-oriented methods are going away from that and moving on to more of these type of patterns where it's just more of data-driven of how it's going to be used rather than how it's modeled in the real world. Spawn functions. Even if we do have different classes for each monster, there are other ways to decorticate. I almost wanted to say decorate, but decorticate, is that a real word? Can I look it up? It is. Posture is an abnormal posturing in which a person is stiff with bent arms, clenched fists, and legs held out straight. I guess I'm not straight, but interesting. This Felis catus. Instead of making separate spawner classes for each monster, we can make spawn functions, like so. So we have a spawn ghost function that returns a new ghost. Right, so instead of this like spawner class, so now we're gonna move away from this, it seems. And so spawn ghost, return new ghost. Let's just create that function. Function spawn ghost. I don't know if it's like part of a class or not at this point in time. So we're just going to return a new ghost like that. Now that could be used here. So instead of this new ghost, we could, for example, take in the health. So the health and the speed, pass that in here. And now instead of this, we could do const ghost prototype equals spawn ghost 15.3. All right, so then this is less boilerplate than rolling in a whole class for constructing a monster of some type. Then the one monster class can simply store a function pointer. So we can pass this the reference to this function around. So now we have a type definition monster. So we're defining a type monster, which is a spawn callback. I don't know if that's called spawn callback, or if it's just, I guess that's the name of the type, and returns a monster? Or is it this class monster? Oh, that's what it is, because it returns. This function returns this. All right. Then we have a class spawner. So we're back to having a class spawner here. Public, we're gonna have a spawner. So the constructor takes the spawn callback. So now it's gonna be a spawn, and we're gonna store that internally. So spawn. Okay, so spawn monster returns this dot spawn. To create a spawner for ghosts, you do spawner, ghost spawner. So now here, we're gonna do essentially push into ghosts. I guess ghost spawner equals new spawner. So instead of this entire thing, it's spawn ghost and a reference to it. Now the problem here is that if spawn ghost needs health and speed, which I guess we shouldn't. We should just say, hey, all new ones start with 15 and 3. And there you go. That's where it's defined, and that's where it's going to be given all the time. Templates. By now, most C++ developers are familiar with templates. Our spawner class needs to construct instances of some type, but we don't want to hard code some specific monster class. The natural solution then is to make it a type parameter, which templates let us do. I'm not sure if C++ programmers learned to love them or if templates just scared some people completely away from C++. Either way, everyone I see using C++ today uses templates too. So I guess, is this going to use templates? Class spawner. So here's our spawner class. We're gonna declaring spawner constructor and the spawn monster. Then they have this template here, which is a class T, class spawner 4, public spawner, monster, spawn monster, return new. Let's see. So I've not used C++, and I've definitely not used templates. This, to me, this pattern makes it look to me like it might be a generic in Rust, or in some other languages that implement generics. I don't know if I'm correct in that assumption. I'm realizing that Pretzel is spamming the chat, so I'm gonna turn it off. Even though it might be nice to have music, it's not nice to spam the chat so much. I might end up paying them money, so that way that doesn't happen. Let's see. Continuing on. So if we have this like generic T, we're creating a new class, spawner4, which has a public spawn monster that returns a new T. Okay, interesting. So spawner4. So in JavaScript, it's weakly typed, so not nearly as big of a problem for us. So if we create a new class, spawner4, I can now extend, I can still extend, this extends spawn monster. No, it extends spawner. We now implement spawn monster in here. And it's going to return a new T. Well, the thing about this is that this spawner already does that for us. Because we can just pass in whatever kind of spawn we want. It doesn't have to be a very specific spawn. So we don't actually need that. Using it looks like spawner ghost spawner equals new spawner4, and we tell it what type it is going to be, and then call that. The spawner class here is so that code doesn't care what kind of monster a spawner creates, can just use it and work with pointers to monster. If we only had the spawner4 class, there would be no single supertype. The instantiations of that template are all shared, so any code that worked with spawners of any monster type would itself need to take a template parameter. First class types. The previous two solutions addressed the need to have a class, spawner, which is parameterized by a type. In C++, types aren't generally first class, so that requires some gymnastics. If you're using a dynamically typed language like JavaScript, Python, or Ruby, where classes are regular objects you can pass around, you can solve this much more directly. In some ways, the type object pattern is another workaround for the lack of first class types. That pattern can still be useful in languages with them, though, because it lets you define what a type is. You may want different semantics than what the language's built-in classes provide. When you make a spawner, just pass in the class of monster that it should construct, the actual runtime object that represents the monster's class. Easy as pie. With all these options, I honestly can't say I found a case where I felt the prototype design pattern was the best answer. Maybe your experience will be different, but for now, let's put that away and talk about something else. Prototypes as a language paradigm. Okay, so after all of this, he admits that, yes, it's important to know it, but he doesn't really use it very often. He can't find good ways. There's other patterns that can take precedence. So it sounds like if we want to use it, we're going to have to sort of force it in. But that might be a little bit, that might be fine. So here with class spawner, it contakes this spawn. So it looks like we're gonna be able to pass in a reference to the class. So we have this ghost class here. So we're gonna have a spawn class. So I might be able to call this spawn. Capital S, capital S, capital S. And then we're going to, when we spawn a monster, call new this dot spawn. Now, something that might be interesting here is that when we have this ghost that has this health, I can set defaults for it. So I can say 15 and 3. So this is JavaScript, for example. And then it will do all of that for us. Then down here, so we have ghost functions. I don't even think we need many of these anymore. Our ghost spawner is going to be a new spawner, and we're going to pass in a ghost, just like that. And now when we call ghost spawner dot spawn monster, it's going to spawn a new ghost for us, which means we don't need this anymore. We don't need, so spawner, we need these like demon and sorcerers and ghosts we need. Clone, however, we no longer need. We no longer need a clone. We just have that. And that does clean it up quite a bit, because now we can focus on updating and changing. Like, we can change demon, and that we don't need to change the ghost spawner at all anymore. The prototype language paradigm. Many people think object-oriented programming is synonymous with classes. Definitions of OOP tend to feel like credos of opposing religious denominations, but a fairly non-contentious take on it is that OOP lets you define objects which you bundle data and code together. Compared to structured languages like C and functional languages like Scheme, the defining characteristics of OOP is that it tightly binds state and behavior together. You may think classes are the one and only way to do that, but a handful of guys, including Dave Ungar and Randall Smith, beg to differ. They created a language in the 80s called Self. While as OOP as can be, it has no classes. Self. In a pure sense, Self is more object-oriented than a class-based language. We think of OOP as marrying state and behavior, but languages with classes actually have a line of separation between them. Consider the semantics of your favorite class-based language. To access some state on an object, you look in memory on the instance itself. State is contained in the instance. To invoke a method, though, you look up the instance's class, and then you look up the method there. Behavior is contained in the class. There's always that level of indirection to get a method, which means fields and methods are different. Right, because the method is here, the instance is here. For example, to invoke a virtual method in C++, you look in the instance for the pointer to its vtable and then look up the method there. Self eliminates that distinction. To look up anything, you just look on the object. An instance can contain both state and behavior. You can have a single object that has a method completely unique to it. If that was all Self did, it would be hard to use. Inheritance in class-based languages, despite its faults, gives you a useful mechanism for reusing polymorphic code and avoiding duplication. To accomplish something similar without classes, Self has delegation. To find a field or call a method on some object, we first look in the object itself. If it has it, we're done. If it doesn't, we look at the object's parent. This is just a reference to some other object. When we fail to find a property on a first object, we try its parent, and so on. In other words, failed lookups are delegated to an object's parent. I'm simplifying here. Self actually supports multiple parents. Parents are just specially marked fields, which means you can do things like inherit parents or change them at runtime, leading to what's called dynamic inheritance. That would be interesting. I guess that also is really helpful for testing as well. Parent objects let us reuse behavior and state across multiple objects, so we've covered part of the utility of classes. The other key thing classes do is give us a way to create instances. When you need a new thingamabob, you can just do new thingamabob, or whatever your preferred language syntax is. A class is a factory for instances of itself. Without classes, how do we make new things? In particular, how do we make a bunch of new things that all have stuff in common? Just like the design pattern, the way you do this in self is by cloning. In self, it's as if every object supports the prototype design pattern automatically. Any object can be cloned. To make a bunch of similar objects, you beat one object into the shape you want. You can just clone the base object built into the system and then stuff fields and methods into it. Clone it to make as many clones as you want. This gives us the elegance of the prototype design pattern without the tedium of having to implement clone ourselves. It's built into the system. This is such a beautiful, clever, minimal system that as soon as I learned about it, I started creating a prototype-based language to get more experience with it. I realized building a language from scratch is not the most efficient way to learn. But what can I say? I'm a bit peculiar. If you're curious, the language is called Finch. So before we continue, JavaScript is a prototypal inheritance language, and that it implements exactly what he's describing here. So, for example, we have our class spawner. This spawn monster is not stored in the class spawner. It's stored in, like, I mean, I guess in a way it's a little bit complicated because classes aren't true classes according to like Java or C++ in this specific instance. Class is oh, Danny Finch. Yes, definitely. Like it is a bird-based language. So if we have the object, we look at the ghost spawner, we create a new one off of spawner. Spawn monster isn't stored inside of this object. It's stored in the parent of this object, which just happens to be this class. And so it looks here, can't find it, then goes up. But if we go up to the top, if spawner doesn't extend anything. If it did extend something from, for example, monster here, if monster creates something, then it would go on up. Unless I'm mistaking that, that's very similar to what's happening here. So prototypal inheritance. Now, I could put a function into the constructor here. So we can put this dot do, we could put spawn monster. So we could do this dot spawn monster equals and create this function like this. And it calls a new spawn. So if I were to do that, now this function is unique to each object. Each object is going to have its own function that is unique. If it got changed for some reason, it would only change for that specific spawner. And that's the difference between putting in a constructor here and putting it down. The classical way to do this would be just to make a function. So to make exactly the same spawner down here, prototypical, I guess not inheritance, but prototypical version of spawner. So we're gonna have a function spawner. It's not taking anything in. Oh, actually no, it does. It takes a spawn in, and we are going to return a new object. And so this actually in this case, we're just gonna say this dot spawn equals spawn, and then we're gonna say what is it? It's spawner.prototype.spawn monster equals, and then it's an actual function. I have to use the function keyword here so we can get this. The arrow function ignores this, which actually, which could have problems. So the function, we're not going to take anything in, and we're going to return a new this dot spawn. And that is like sort of the old style of JavaScript programming that we would have to do when we wanted to create class-like things. How did it go? I was super excited to play with a pure prototype-based language, but once I had mine up and running, I discovered an unpleasant fact. It just wasn't that fun to program in. I've since heard through the grapevine that many of the self-programmers came to the same conclusion. The project was far from a loss, though. Self was so dynamic that it needed all sorts of virtual machine innovations in order to run fast enough. The ideas they invented for just-in-time compilation, garbage collection, and optimizing method dispatch are the exact same techniques, often implemented by the same people, that now make many of the world's dynamically typed languages fast enough to use for massively popular applications. Sure, the language was simple to implement, but that was because it punted the complexity onto the user. As soon as I started trying to use it, I found myself missing the structure that classes give. I ended up trying to recapitulate it at the library level, since the language didn't have it. Maybe this is because my prior experience is in class-based languages, so my mind has been tainted by that paradigm. But my hunch is that most people just like well-defined kinds of things. In addition to the runaway success of class-based languages, look at how many games have explicit character classes and a precise roster of different sorts of enemies, items, and skills, each neatly labeled. You don't see many games where each monster is a unique snowflake, like sort of halfway between a troll and a goblin with a bit of a snake mixed in. Well, I mean, I was gonna say like maybe some of the roguelikes, right? Where you don't have to have any kind of like graphical interface. It's just, you know, keys on a keyboard. But like the one thing where I do see like lots of unique snowflakes are like items in RPGs. So for example, like Diablo 2 propounded to have like billions and billions and billions of possible items. The only way they're doing that is by mixing things together in some kind of like random order. While prototypes are a really cool paradigm, and one that I wish more people knew about, I'm glad that most of us aren't actually programming using them every day. The code I've seen that fully embraces prototypes has a weird mushiness to it that I find hard to wrap my head around. It's also telling how little code there actually is written in a prototypal style. I've looked. What about JavaScript? Okay, if prototype-based languages are so unfriendly, how do I explain JavaScript? Here's a language with prototypes used by millions of people every day. More computers run JavaScript than any other language on Earth. Danny Fritz, JavaScript, when everyone used prototype for classes, was pretty bug prone and hard to fix. Yeah, that's true because that is very true. Classes do make things easier to understand what's happening. And I think there's a lot of people that were sort of programming this way and just copy pasting from Stack Overflow or other code and not really understanding what was happening. Brendan Eich, the creator of JavaScript, took inspiration directly from Self, and many of JavaScript's semantics are prototype-based. Each object can have an arbitrary set of properties, both fields and methods, which are really just functions stored as fields. An object can also have another object called its prototype that it delegates to if a field access fails. As a language designer, one appealing thing about prototypes is that they are simpler to implement than classes. I took full advantage of this. The first version of JavaScript was created in 10 days. But despite that, I believe that JavaScript in practice has more in common with class-based languages than with prototypal ones. One hint that JavaScript has taken steps away from self is that the core operation in a prototype-based language, cloning, is nowhere to be seen. There's no method to clone an object in JavaScript. The closest it has is object.create, which lets you create a new object that delegates to an existing one. Even that wasn't added until ECMAScript 5, 14 years after JavaScript came out. Instead of cloning, let me walk you through the typical way you define types and create objects in JavaScript. You start with a constructor function. Object assign. So Danny in chat is saying, well, what about object.assign? And then you have we have a new object, that's the target one, and then we have the other one, which I guess in this case would be ghosts 0. It's like the first ghost. That will totally clone this object, right? The problem, of course, is that it's a object.assign is still a surface clone, a light clone, shallow. That's the right word. It's a shallow clone. So if there is any methods or any arrays or objects inside of this instance of Ghost, then we run into problems again, which is then where you find people, possibly like me, doing crazy weird stuff like, hey, let's do json.parse and wrap that around json.stringify this ghost. Yeah, totally got it. Yep, perfect. No problems. That will deeply clone it. I wouldn't do that. I'd probably use a clone from Lodash these days. All right, so you start with a constructor function. So function weapon, range and damage, this at range, this at damage. This creates a new object and initializes its fields. You invoke it like var sword equals new weapon. So we sort of went over that with this spawner here. The new here invokes the body of the weapon function with this bound to a new empty object. The body adds a bunch of fields to it, and then the now filled in object is automatically returned. The new also does one other thing for you. When it creates that blank object, it wires it up to delegate to a prototype object. You can get to that object directly using weapon.prototype. While state is added in the constructor body to define behavior, you usually add methods to the prototype object. Something like this. Weapon.prototype.attack equals function, the target, and then you do a bunch of logic to determine what you're doing. And that adds this function to the prototype. This adds an attack property to the weapon prototype, whose value is a function. Since every object returned by new weapon delegates to weapon.prototype, you can now call sword.attack, and it will call that function. It looks a bit like this. Okay, so we have our weapon prototype, attack other methods, and then our sword, which has the prototype, which points to the weapon.prototype, and also all of its properties. Let's review. The way you create objects is by a new operation that you invoke using the object that represents the type, the constructor function. State is stored on the instance itself. Behavior goes through a level of indirection, delegation to the prototype, and is stored on a separate object that represents the set of methods shared by all objects of a certain type. Call me crazy. That sounds a lot like my description of classes earlier. You can write prototype-style code in JavaScript, sans cloning, but the syntax and idioms of the language encourage a class-based approach. Personally, I think that's a good thing. Like I said, I find doubling down on prototypes makes code harder to work with. So I like that JavaScript wraps the core semantics in something a little more classy. Prototypes for data modeling. Okay, I keep talking about things I don't like prototypes for, which is making this chapter a real downer. I think of this book as more comedy than tragedy, so let's close this out with an area where I do think prototypes, or more specifically, delegation, can be useful. If you were to count all the bytes in a game that are code compared to the ones that are data, you'd see the fraction of data that has been increasing steadily since the dawn of programming. Early games procedurally generated almost everything so they could fit on floppies and old game cartridges. In many games today, the code is just an engine that drives the game, which is defined entirely in data. That's great, but pushing piles of content into data files doesn't magically solve the organizational challenges of a large project. If anything, it makes it harder. The reason we use programming languages is because they have tools for managing complexity. Instead of copying and pasting a chunk of code in 10 places, we move it into a function that we can call by name. Instead of copying a method in a bunch of classes, we can put it in a separate class that those classes inherit from or mix in. When your game's data reaches a certain size, you really start wanting similar features. Data modeling is a deep subject that I can't hope to do justice here, but I do want to throw out one feature for you to consider in your own games: using prototypes and delegation for reusing data. Let's say we're defining the data model for the shameless gauntlet ripoff I mentioned earlier. The game designers need to specify the attributes for monsters and items in some kind of files. I mean, completely original title, no way inspired by any previously existing top-down multiplayer dungeon crawl arcade games. Please don't sue me. Or I guess the author. One common approach is to use JSON. Data entities are basically maps, or property bags, or any of a dozen other terms, because there's nothing programmers like more than inventing a new name for something that already has one. We've reinvented them so many times that Steve Yegg calls them the universal design pattern. So a goblin in the game might be defined something like this. So we have an object, name, min health, max health, resists, and weaknesses. And it's just a plain object. This is pretty straightforward, and even the most text-averse designer can handle that. So you throw in a couple sibling branches to the goblin family tree. Okay, so now we have a goblin grunt. Now we have a goblin wizard that also has spells, but besides that, looks like exactly the same. And a goblin archer that has attacks with a short bow instead of spells. Now, if this was code, our aesthetic sense would be tingling. There's a lot of duplication between these entities, and well-trained programmers hate that. It wastes space and takes more time to author. You have to read carefully to tell the data is even to tell if the data even is the same. It's a maintenance headache. If we decide to make all the goblins in a game stronger, we need to remember to update the health of all three of them. Bad, bad, bad. If this was code, we'd create an abstraction for a goblin and reuse that across the three goblin types. But dumb JSON doesn't know anything about that. So let's make it a bit smarter. We'll declare that if an object has a prototype field, then that defines the name of another object that this one delegates to. Any properties that don't exist on the first object fall back to being looked up on the prototype. This makes the prototype a piece of metadata instead of data. Goblins have wordy green skin and yellow teeth. They don't have prototypes. Prototypes are a property of the data object representing the goblin and not the goblin itself. With that, we can simplify the JSON for our goblin horde. Okay, so we have an object, the name goblin grunt. It has a min health and max health. It resists, and it has its weaknesses. And then we have our object, which is the goblin wizard. So everything that's unique about it is recreated. So its name is goblin wizard. Its prototype has name goblin grunt. And spells, it has unique here, and Goblin Archer is the same, it just has attacks. Since the Archer and Wizard have the Grunt as their prototype, we don't have to repeat the health, resists, and weaknesses in each of them. The logic we've added to our data model is super simple. Basic single delegation. We've already gotten rid of a bunch of duplication. One interesting thing to note here is that we didn't set up a fourth base goblin abstract prototype for the 3 concrete goblin types to delegate to. Instead, we just picked one of the goblins who is the simplest and delegated to it. That feels natural in a prototype-based system where any object can be used as a clone to create new refined objects. I think it's equally natural here too. It's a particularly good fit for data in games where you often have one-off special entities in the game world. Think about bosses and unique items. These are often refinements of a more common object in the game, and prototypal delegation is a good fit for defining those. The magic sword of head detaching, which is really just a long sword with some bonuses, can be expressed as that directly. So its name, sword of head detaching, its prototype is a long sword, and its damage bonus is 20. A little extra power in your game engine's data modeling system can make it easier for designers to add lots of little variations to the armaments and beasties populating your game world. And that richness is exactly what delights players. And that's the end of this chapter. So what's interesting is that he goes through and says, oh, it's super good to know this pattern. And at the end, it's like, well, but don't use it. Don't use it in its natural state. He then talks about using the knowledge you gain from knowing the pattern into the data side of